Okay, we have here on the board this identity with the dilogarithm. We've got dilogarithm of z plus dilogarithm of 1 over z is going to be minus pi squared over 6 minus natural log of minus z all squared over 2. This is very similar to an identity I did recently where we just had minus z. So in order to go between those, you really can just do a substitution and plug in a minus z everywhere, and that's going to reverse the sign over here. We have over here to the right two definitions for the dilogarithm. We've got our series definition here at the bottom, but then we've got our integral definition up top that we're going to use here. Now, there's a long way to do this. You could actually just, because we have an integral definition, you could go and just integrate both these and come to this. But I'm going to do it a shorter way. I'm going to create a function out of all this stuff. And it's going to be in terms of z. So we're going to have our function in terms of z that we're going to start with. And then when I do this, let's put this into the integral notation. So for this is exactly this right here. So we're going to have minus integral from 0 to z ln 1 minus x over x. For this next one here, we just need our input on it to be 1 over z. So that'll be our upper bound there. And I didn't plan my space very well, but we already used this definition. So let's get rid of both these and just go ahead with it. So then I'm just going to bring these onto the other side of the equation. And what's going to happen, we're going to have plus pi squared over 6 and plus this thing right here. And then from here, all I want to do is let's differentiate this. So we want to get our f prime of z value. And to differentiate integral, this is just going to be fundamental theorem of calculus. We can just plug in the z. So this is going to become ln 1 minus z over z. You do need the chain rule when you do this, but derivative of z is just 1, so we can leave that off. We don't worry about that. So we plug in 1 over z here, same kind of thing, ln 1 minus 1 over z. Then plug into the denominator, we get 1 over z. Chain rule on this, that's going to be minus 1 over z squared, just taking the derivative. Here, derivative of pi squared over 6, a constant, that's going to be a 0. Derivative of this, we have the 2 in the denominator as a constant. First, using power rule on this, we're going to have the 2 come out front, natural log minus c. Then chain rule, derivative of ln minus c is going to be 1 over minus c. Chain rule again, that's going to create a minus 1. Let's just use it to change the sign over here. And then clean things up. Over here, minus times minus is plus. 2 over 2 is a 1. Over here, we can do minus times minus is plus. If I multiply this in here, z squared times 1 over z, we can just make this a z right here. Now, let's clean up 1 minus 1 over z. Let's get a common denominator on that. So for the 1, I can write it as z over z. So we'll have z over z minus 1 over z. Put that together, common denominator, z minus 1 over z. What I want to do to get it to line up with everything else going on, because we've got 1 minus z over here, so I want to reverse the sign and everything. So if I reverse the sign in the numerator, 1 minus z, I need to reverse it in the denominator and write it like this. And so we'll use this value right here. I'm just going to plug it back in right here. And then now I'll go ahead and rewrite this thing. But what's going to happen for that, with log properties, I can split that up. So we've got this first one. For this one, breaking it into 2 pieces, we get natural log 1 minus z over z. Then for the denominator, we'll bring a minus sign with the log property. So it's going to become natural log minus z over z. Then here, like the 0 is going away, this stuff's going away. Bring this thing here down. We got natural log minus z over z. And then here's the payoff. This is the same thing as this with a minus sign. So this cancels to 0. Same thing here, this cancels to 0. Everything's 0, and what we get is f prime of z is just equal to 0. So now what that implies, for a derivative to be 0, that tells us that our function needs to be a constant. You think about it either way. When you differentiate a constant, you get 0. When you integrate a 0, you get a constant. So we'll take this and come back up here, and we're saying this whole thing is going to be a constant. But what we really need is for this constant to be 0, just basic algebra. If you have x equals y, then x minus y equals 0. So what we need to do is we need to show that this constant is going to be a 0. Well, what that's going to allow us to do is we can evaluate our function at any point. Because we know our function's a constant, the graph's just a line like that, So it has the same value, of course, at any point. I know I'm kind of overkilling this, but we can evaluate at any point and we're going to get the same value if I evaluate it here. So we can choose whatever z we want, get the constant, and we need that to be 0. So the convenient value I want to use on this is going to be z equals -1. The reason is that's going to fix this natural log, because then we have natural log of 1, and that's going to go away. So if we plug in, just remembering this is the same thing as this is the same thing as this. So you plug -1 in here, you got Dilogarithm -1, plus over here, you plug in -1, again, 1 over -1, that's going to be -1, plus pi squared over 6. And like I said before, you plug a -1 and this last part's just a 0. But we can put these two things together and we get 2 times Dilogarithm -1 plus pi squared over 6. But this thing has a well-known value. We found this in a previous video, and it's just going to be minus pi squared over 12. But 2 times minus pi squared over 12 is going to be minus pi squared over 6 plus pi squared over 6, and that equals 0. That's what we wanted to show. Our constant 0, so this identity is going to work. Okay, so really useful identity, and as we'll see in some future videos, it can be pretty hard to derive values of the Dilogarithm. So that's why we need all these different functional equations and identities, because, I mean, actually some values might be impossible to get at, but even other values can be just difficult to derive. So we do need all the identities we can get. Okay, that's it for today. Thanks everyone for watching. Have a good day.